Hello student, very good morning to all of you. I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the rearrangement reaction, and in that we have learned two main important rearrangement reaction. One is a Hofmann rearrangement reaction and second one is a Lawson rearrangement reaction. What are the starting material, what are the reagent, and by involving nitrine to isocyanate, what kind of the product they are producing. So that what are the condition, how the starting materials are obtained. So that type of the thing we have discussed so far. So today we are going to discuss the remaining rearrangement reactions. So number 3 now. So number 3, this is also as the same kind of the reaction we are talking, because there is a formation of nitrine and nitrine is converted into as a isocyanate, and that isocyanate after the hydrolysis resulting into as a formation of the amines. So same kind of the reaction we are talking, but there are different type of the starting material and the different reagent, specific selective reagent used, and how we are getting that type of the compound. So that we are talking, and one we have seen Hofmann rearrangement reaction, and then second one is a Lawson rearrangement reaction or Lawson route. Now is a Curtius route we are talking about. Curtius route. Curtius route are the Curtius rearrangement reaction. What is the actual? So what are the starting material is used here for this rearrangement? Why it is called as a Curtius is the scientist name. He discovered first time this kind of the reaction, and that's why name is given to that reaction is a Curtius rearrangement reaction. And acyl azide RCON3 is prepared in case of the two ways reaction of an acyl chloride with sodium azide. This is the one way to convert that nitrine into as a nitrine. What they have taken in a Curtius, starting material is taken, let us see as a general reaction. I am taking over here acyl chloride. Let us see over here this one. Suppose they have taken as a C11H23 C double bond OCl, that type of the thing. But I am taking here only as a general reaction, which can you understand the actual meaning of acyl, that acyl chloride. Here are C double bond O, then Cl, right? This is a starting material I am taking over here for Curtius rearrangement reaction. The name of this compound is acetyl chloride, right? Acetyl chloride, or what we can call it as a general acetyl chloride. Okay, acetyl chloride. That type of the compounds are there. Or C double bond O. Now this will be treated with sodium azide NaN3. NaN3, remember NaN3, which is a sodium azide. This is called as a sodium azide. Sodium azide. So this is the name of this reagent, and this reagent is used for this, and this is treated with at first one, and second one is heated at 60 degrees centigrade, and that produce the compound R C double bond O, then N3, that type of the azide. Now N minus, it is act as a nucleophile nucleophile is going to attack over there, and now this compound we can represent like this, RC double bond O, then we can write this N double bond N double bond N. Here you can write as a positive charge, here maybe as a negative charge, and here which is a lone pair, because normal bond number of bond present in that nitrogen atom are the 3, and therefore lone pair is present over there. And this compound we can represent in this manner, this negative charge coming over there, and then this negative charge over there. So we can represent this structure like this, R C double bond O, then N minus, then N triple bond N. Look at, here is a positive charge over there, right? Now this structure we can represent like this. This is a resonating structure, or what we can call it as a it is shown by double-headed arrow. The meaning of that double-headed arrow, two different structure, the two different ways to draw the same delocalized structure, because the electrons which are not localized but they are delocalized. So for that purpose, or for such a representation, we are showing as that double-headed arrow. Now once it is if you look at carefully, what you see, this nitrogen is a nitrogen case. So here what is happening, this R group, now actually rearrangement occurs here, right? Rearrangement, wow, this R group is attached to that nitrogen atom, this negative charge forming as a double bond over there, and this revolving around it, and there is a evolution of that nitrogen atom. The mainly N2 get evolved over there, and here you are going to get as a species, here N double bond, then C double bond O. This is the species which we got. This is nothing but as a isocyanide. This is nothing but as a isocyanide. It is a species which we got over here. So this Rn double bond C double bond O N2, so we got over here. So this is a isocyanate, that is a species we got, and that isocyanate, this isocyanate and further treated with water, as we know that H2O, when that OH is going to attack on this and then H here, so you will be getting here RNH, then C double bond O, and generally we are writing that OH for the sake of convenience. Now what is going to happen after the heating, which we have heated at 60 degrees centigrade, what is going to happen? There is a evolution of carbon dioxide, and final product is obtained as a amine NH2 and plus carbon dioxide, and that goes in the atmosphere. This is a general representation of this ammonia, this Curtius rearrangement. Understood this one? What is this acetyl chloride? From where we are getting? This is getting from the acetic acid. A general formula of what we can call it as carboxylic acid, monocarboxylic acid, RC double bond OH, if it is treated with thionyl chloride, PCl5, PCl3, the resulting compound is formed as a acyl chloride, not this, acyl chloride, and acyl chloride further treated with sodium amide, and that gives you this type of the curve. This one is a negatively charged, it is going to attack over there, revolving around it, and the Cl get evolved during this process, and we are getting as a such type of the things over there. Now the example which is given in the book that we are going to consider over here, and let's see how that example, because we know, once you know the mechanism And mechanism, as I already told you, that practice makes the man perfect, so that you practice a lot while writing that type of the mechanism, and then you will be very expert in writing those mechanism. Let us see here C11H23, then C double bond O Cl. So that is the compound they have taken here, which is given in the book, that is called as acyl chloride, right? So example here is acyl chloride, this acyl chloride which we have taken over here, and now this one is treated with sodium amide Na(N3). This is the first reagent, and second reagent will be the 60 degrees centigrade, that is the temperature applied here for reaction or for this condition. And what they have got, then this is what we can call it as a nucleophile. Nucleophile is easily attack on that chloride, and we sodium chloride as a salt side product, don't think about that side product, but here we are getting C11H23 and C double bond O N3, right? That is a N3 azide group is attached to that carbonyl group, which is a good nucleophile. Now this structure we can represent like this: C11H23, then C double bond O, then now N double bond N. Here we can put as a negative, here is a positive, and lone pair present on that nitrogen, they are as it is. Now this further, when we can draw the resonating structure, the meaning of this arrow, there are two ways to draw the same delocalized structure. Now this we can represent in this way also. So same structure we can draw like this: C11H23 C double bond O, then N minus, then N positive charge remains as it is, and there will be a third 3 triple bonds are there, and that's the driving force behind it. For rearrangement reaction, there is a evolution of nitrogen atom over there, and therefore rearrangement reaction occurs. This group particularly, what is going to happen? This negative charge comes here forming as a double bond. The electron revolving means this double bond around that carbonyl remains as it is, but it is pushing this group from here to here, and there is a departure of nitrogen atom. So that is the speciality of that Curtius. What will be the gas evolved during that Curtius rearrangement reaction? Remember, there is a nitrogen gas is evolved during this process, and we are getting this one C11H23, then N double bond C double bond O. This is the species we got, isocyanate, which is a species which is a intermediate obtained over there, and this is during that hydrolysis. H2O, this lone pair attacking on that carbonyl carbon, and there will be the NH, and then we are getting C11H23, then N minus over there, and C not N minus. Here the hydrogen atom which is available here in the water, it connect to that nitrogen atom, and now generally we are representing this OH is like this, and after the heating, like as a 60 degree, there is a evolution of carbon dioxide, and we are getting C11H23, and what we can call it as a NH2, that amine, and there is a evolution of carbon dioxide. So this is the general representation of this Curtius rearrangement reaction which we have generally seen over here. So this is about the reaction of azide or the Curtius rearrangement reaction. Understood this one? The thermal or photochemical rearrangement of acyl azide into amines via isocyanate is an intermediate, and while the thermal rearrangement is a concerted process, the photochemical rearrangement goes through a nitrene intermediate. So that type of the reaction just now we have seen. Let me check whether you are able to predict the product or not, and whether you are going to recognize the reaction, what type of the reaction. Generally, when we are discussing that the heading which is given, you can easily recognize this reaction. But let me give some more examples. C6H5 C double bond O, then Cl, that is a benzoyl chloride, and which is there, and then when it is treated with sodium azide Na N3, what type of the product it gives? It gives generally C6H5, then C double bond O, then N3, and this N3, these three line represent the equivalent structure of that. So we are getting C6H5 C double bond O, N double bond, N positive charge over there, negative charge, and lone pair which is present on the nitrogen atom. And now what is going to happen here? This structure we can draw in another way also, and while drawing the structure in another way, we generally shown as a double-headed arrow like this. And so what it gives? The negative charge forming as a double bond over there. Negative charge comes on that nitrogen atom, C6H5 C double bond O, N minus charge, then N triple bond, N, here is a positive charge. So that is a representation of that. And this now what is going to happen? Next one actual the rearrangement reaction taking place over there. This negative charge forming the double bond between carbon atom and this nitrogen atom, and this double bond revolving around it, and at the same time this phenyl group migrated from here to here, and this nitrogen gas is evolved during this reaction. So N2 is evolved, and then next one we are going to get C6H5, then here is a N double bond C double bond O, and the species which we have obtained over here is nothing but isocyanate, and the isocyanate as an intermediate we are getting in the Curtius rearrangement reaction. And finally, when it is treated with water, what is going to happen? It is going to attack on that carbon, and we are going to get here C6H5, then NH, then C double bond O, and OH we can show like this over here. And after that heating, what you are going to get? There is a evolution of carbon dioxide and the formation of aniline here, C6H5NH. This is nothing but as a aniline which we got here, and then carbon dioxide is evolved during this process. This is a general representation of the that Curtius rearrangement reaction. Now let us move on to the next reaction which we are going to learn, that is a fourth one, which is known as a Sem-IV rearrangement reaction, right, or the Sem-IV rule. What would be the difference or distinction between what we can call it as a Sem-IV and the Curtius rearrangement reaction? They are in the same, but let us see here fourth one, which is that is called as a Schmidt rearrangement reaction. SCHMIDTS, Schmidt rearrangement reaction, or what we can call it as Schmidt root, ROUT, root, because after that we will see later on. But the Schmidt root or the Schmidt rearrangement reaction, how it takes place, I think before starting as a Schmidt rearrangement reaction, I have forgotten one of the way in that Curtius rearrangement reaction. Let me discuss that point. The reaction of an ester with excess of an hydrazine followed by reaction of the acyl hydrazide produce product RCONH NH2 with cold nitrous acid. Acyl azide decomposes to isocyanate on heating. So that is a general reaction can take place over there, and let me give that also. Generally as an ester, if it is present over there, let us see here. That is a second way of Curtius rearrangement reaction starting from the ester. I am taking as a general reaction here RC double bond OAC. Ester is a starting material, and that will be treated with what we can call it as a hydrazine hydrate, that is H2N NH2, that is similar to as a azide derivative. So what you are going to get? You are going to get R C double bond O, then NH2. That is the compound hydrazine hydrate derivative we got over here, and now this is further treated with what is the reagent, that is HNO2, nitrous acid. When nitrous acid is treated over there, what it gives? It gives the formation of that RC double bond O, then isocyanate type of the intermediate is obtained. When it is treated with that one, we are getting here N double bond C double bond O, isocyanate, and further that isocyanate is further treated with what we can call H2O, and it gives the product RN, because this is going to attack on that as usual RNH, then C double bond O, OH we can write like this, and after that if you heat it, what is going to happen? This moving like this, there is a evolution of carbon dioxide, and resulting compound is formed as a RNH2 plus CO2, carbon dioxide that goes in the air. So this is the second way of representing the Curtius rearrangement reaction. Now let us move on to the fourth reaction, which is one of the famous reaction, that is called as the Schmidt rearrangement reaction. So that is the reaction which we are learning over here. Now third one, not third one, I think fourth one, the reaction number fourth one is the Schmidt rearrangement. Schmidt rearrangement reaction, or Schmidt root you can call it. Schmidt root or Schmidt rearrangement reaction. Here also the starting compound is a acetic acid. It is starting from as a acetic acid, RC double bond OOH, and that will be treated with, suppose as a hydroxyic acid. Here we are treating with HN3, that is a hydroxyic acid, and what you are going to get, the product which we are going to get RC double bond O and N3. That is the product generally obtained over here, and this the reaction, then hydroxyic acid, the H is going to attack over there, and we will get this one. Now this, and as we know that this is a general reaction, similar to as a which we have learned just now in case of the Curtius reaction. Curtius reaction and this reaction has a similarity, only the reagents are different, but the reagent, remember in a Smith rearrangement reaction, the reagent is used as this one, that is called as a hydroxyic acid. Most of the students get confused over there. They are thinking that HN3 may be as a ammonia. Remember, ammonia means what? NH3. This is called as ammonia. I already explained you ammonia, right? And but HN3 is called as a hydroxyic acid. Hydroxyic acid. This is the acid, and this is the basic in nature, and this is acidic in nature. That is the major difference between these two. Formula looks as a very similar, and that's why most of the students get confused. But remember, while learning this, I am telling again and again, HN3 is a hydroxyic acid. This is acidic in nature, and acidic in nature we know that they has tendency to donate the proton, but base, what the base has a tendency, they can accept the proton according to as a what we can call it as a that there are different theories which we already learned. So, but here remember this we can, the name of this compound is hydroxyic acid. That you have to remember. And in a earlier rearrangement reaction, in a Curtius rearrangement reaction, where we use the reagent is a sodium azide, and rest of the thing is as it is. There is, but the major difference, there we are using as a sodium azide as a salt, as a reagent, and the reactions performed and we got the product. But here we have used as a hydroxyic acid, protonate first. This carbonyl group becomes as a more what we can call it as a deficient in nature. And once you got this one, and as we know that R C double bond O, then we can represent this double bond N, double bond N, minus charge, positive charge you can put here, and lone pair. Why I am putting as a positive charge in the middle nitrogen atom? Look at carefully, what do you see over here? 1, 2, 3 and 4 bond present over there, and therefore positive charge on that nitrogen atom, and this is a this is the arrow. This arrow is called as a resonating arrow. Two different ways to draw the same delocalized structure. So that is the meaning of this arrow, and according to that we can represent this molecule like this C double bond O, then N means this negative coming over there, and then this nitrogen has a negative charge, middle nitrogen has positive charge. Still, why it has a positive charge? Look at here again, 3 bond and 1 bond, so positive charge remains throughout. And now the actual rearrangement reaction takes place over, and after the rearrangement this R is attacking to that nitrogen atom, negative charge forming as a double bond over there, and this double bond I am showing as a this way. It means that double bond with that carbonyl group remains as it is, and there is a departure of that nitrogen atom. Here in the Smith rearrangement reaction also there is a driving force is the evolution of the nitrogen atom, and therefore we are getting as a N2 that goes in the atmosphere, and plus we can write here R N double bond C double bond O, right? This is isocyanate derivative, isocyanate, which is a derivative which we got over here, and this further treated with water, H2O, hydrolysis reaction carried out, and you are going to get here RNH, then C double bond O, OH we are representing like this, and after the heating what is happening over there, this is the way of evolution of carbon dioxide, and the resulting compound is a amine plus carbon dioxide. So that is the reaction will take place over there, and this is the reaction which we have seen over here. And now in the Schmidt rearrangement reaction, and if you talk about the stereochemistry of that, it retained as it is. Let us see how the stereochemistry is retained in this Schmidt reaction, and this is a modification of the Curtius rearrangement in which a carboxylic acid is heated with hydroxyic acid HN3 and an acid catalyst. So let us look at that Schmidt rearrangement reaction which is given in the textbook. Let us see that one, how it is takes place over there. So let us see how we can represent the starting compound. Generally, here is a C, one hydrogen atom we can show over here, then one normal bond which we can show over here is a CH-3, and here there is a what we can call it, here is a pH which is above the plane, and now there is a acid C double bond O, then what we can call it as OH over there. And when it is treated with HN3 is a hydroxyic acid, what is going to happen? This negative charge is going to attack over there, and there is a evolution of water molecule, and that gives here this CH3. This we are representing in the general plane, and that hydrogen atom goes below the plane and pH is above the plane. This is the chiral center, and as we know that chiral center means what? The carbon atom carrying 4 different group is known as a chiral carbon, and which is here, and that chiral carbon there is no bond breaking still over there, and now here N3, and now this N3 we can represent like this, C, then CH3, other rest of the group we are keeping as it is here pH, then here C double bond O, now here N double bond, N minus charge over there, positive charge there, and lone pair I am putting on this carbon atom, and this we can represent, that is a resonating structure we can draw here. Here CH3 methyl group I am writing as it is, hydrogen atom, and then there will be a pH, then C double bond O, then here N, then negative charge on this nitrogen atom, middle nitrogen atom still has a positive charge, and now there is a rearrangement reaction actually occur over here. What is going to happen? This group, the center, the chiral center, whatever, if it has a R configuration, it remains as. If it has a S configuration, the configuration S and R are the absolute configuration. They are remains as it is, means they retain as it is. Only this group is migrating. So this way, like this, and there is a driving force to evolve the nitrogen atom, and finally we are going to get here this CH3, and here now the dotted line hydrogen atom, and there is a pH over there, and now we can show over here this is a nitrogen atom double bond C double bond O, that is nothing but as a isocyanate, which is the intermediate which we got over here, and after the hydrolysis what is going to happen? This is going to attack over there, and you may get over here this CH3 as it is, which is a hydrogen atom, and there is a phenyl group pH, and then NH, then C double bond O, and O we can write like this, and after the heating what is going to happen? There is a evolution of carbon dioxide, and you are going to get this one. Suppose this CH3, that what we can call a hydrogen atom, and this pH is as it is, and NH2, means that configuration is retained as it is. Whatever, there is no change in the configuration, it remains as it is. I think with this let us stop today here. Remaining rearrangement reaction we will see in the next time. Thank you. Have a nice day.